So welcome back, those of you who weren't here for the Great Industrial Talk this morning. What we're going to do the next hour is pretty much to get back to the theme of the entire conference, but also continue Eng Lim's talk and really discuss this thing about data versus computing. Because I'm not that old, but sometimes I start to feel that I'm a bit of an old dog, that there are all these youngsters and they're overtaking you with big data and everything, and they do remarkable things, and then we mutter and say, well, there are things big data can't do. On the other hand, we're also seeing increasingly that big data need very large machines, they need the network and everything, and a whole lot of things that even we do with simulations, suddenly we realize we need big data approaches to start to mine data. So one could certainly argue that there is some convergence here. But the point of this panel is not just to agree on everything, but actually let's try to find some of these conflict points as we as scientists needs to push. What are the challenges emerging in these areas? What are the areas where we definitely should not be using big data because it's not as good as the partial differential equations and vice versa? So to help us with this, we have 4 awesome speakers here who are going to share their opinions with you. I hope that they're not going to agree on everything because then it's going to be a bit boring, and then Florina and I will try to be provocative. But just to introduce them, Eng Lim again gave the talk this morning, CTO at Hewlett-Packard Enterprises. We have Nuria Lopez here on my side, who's a professor of chemistry at Barcelona. We have Matthias Schaffler, who's professor of physics at the Max Planck Institute. And we have Thorsten Schwede, local from University of Basel, who is life science expert. So this spans all the way from super applied life science things into fairly fundamental physics and even industry. So I figured that we should kick this off by having them introduce themselves very briefly, telling them who they are, what they're working with, and what they see both as the problems and challenges and really fun things in science today. Should we start with Nuria?
Yeah. Thanks, Eric. So I'm Nuria Lopez. I work in a research center 100 kilometers south from Barcelona. And what we do is molecular simulations to understand materials that can serve to enhance the processes in the chemical industry, to be more green, selective, active, and you name it.
Matthias?
So my name is Matthias Schäffler. I'm from the Fritz Haber Institute in Berlin, but I think I'm here in representing the NOMAD Center of Excellence, where NOMAD stands for Novel Materials Discovery, which somewhat is, in more general ways, what I would call is computational material science and engineering. One of the few aspects which was missing in your talk, materials. But this is actually a very important field in the sense that if you really think about it, be it medicine or be it the lifestyle or be it the prosperity of our society, it very much really depends on new materials. And it's supported very much in the US and in China. In America, there is this White House initiative, which is called the Materials Genome Initiative for Global Competitiveness, to keep the American industry strong in materials. And so there's a lot of actually funding in this area. And we will see actually how you can do with this in computing and in fact in data in this discussion.
Thorsten.
Hi, my name is Thorsten Schwede. I'm originally a chemist from structural biology. I've moved relatively early into protein structure modeling and prediction, which kind of sparked my interest in computation. And over the years, I stayed in the area of predicting and working with health data. For the last years, I got involved in something called the Swiss Personalized Health Network. And there, the idea is that we try to use what we actually know about us humans from our daily life, from our treatment in clinics, and make it available again to research. Because we heard in a brilliant keynote this morning how much fun you can have if you can choose your topic and you apply your methods in areas where they work well. Now that luxury we don't have when we try to understand human bodies, human development, and human disease. And we have to deal with the data that is around there with all the shortcomings of it. And nevertheless, it's an important topic, so we're trying to come up with ways of improving human health using computational techniques.
And Eng Lim, even if you gave the preceding keynote, there might be some people here who
So did
took
you
it late
predict
morning.
this?
Predict the
rain?
rain, is it? Only San Francisco Airport. Yeah.
Okay.
More recently, although My role has always been high-performance computing, but more recently, the applications have included machine learning, as you've seen in the talk, and being applied for farms, pharmaceuticals, more recently also, and of course, the financial industry. A lot of my time also is spent going out, giving speaking engagement like this. But to me, I also learn a lot in the process, right? It's through these conferences that I hear these different views that, therefore, I make my adjustments, in my next talk appropriately. So I really appreciate this, learning from you all.
So I'll kick off with one provocative question right away. Based on this morning and everything we heard and everything we hear about all the time, we're all so amazed with what we can do with data analytics and everything, right? Does this mean that it's time to throw scientific computing overboard and we should change the name of PASC to Platform for Advanced Data Analytics instead? Well, Matthias, like your area, it's probably one of the largest users of supercomputing power historically, right? And it seems like you're all switching over to data now.
Pretty well, yeah.
Yeah. Is computation the past or?
How to answer that? Actually, let me recall what we wrote in the original NOMAD proposal in 2014, which also was actually meant to be exascale, but actually exascale only was in one sentence. The sentence basically is the reason and the only reason why we do computation is that we want to create new data. High-performance computing, in particular exascale computing, only makes sense if you can also deal with the data. And so big data, I think, is not a game change, which somewhat the title provocative wanted to suggest or argues. It's not a game change, but big data is needed to some extent. It's an overdue component in fast computations. Some HPC centers have realized that already, but in general, I think the big data challenges have not been considered properly. I mean, big data challenges means dealing with the data, searching data, analyzing data, doing artificial intelligence. I think it's certainly a component of HPC computing because computing creates data and data should be used, right? And they should be used in the new way. I mean, they should be used in the traditional way that you calculate a certain quantity, but they should be used in the way which we heard in the previous talk, that you look, there is more structure in data. I mean, data have structure by itself, and identifying the structure by artificial intelligence, and after you have found structure, then you look into what is the reason of this structure. What can I really predict from that? That is, I think, also part of the new HPC computing, I think.
Just to add on this, in a field like is so heterogeneous as our field, I would say that we are still very much concentrating on the data coming from computations. And it would be extremely nice if we could incorporate all the knowledge that comes from real practice, from real synthesis, from real spectra, I mean, the ways that they have to store the information, the particular scientific information. And none of us is doing anything related to this still, because this is far too challenging.
But
It wasn't computing challenging, and we were driving the development of faster and faster and faster and faster computers. We were probably blindsided by the fact that data is the next wave, or that these computations will produce so much data. So will we have to take a similar approach to tackling the data challenge as we did with the compute challenge over the years? Do we need high data processing machines? Do we need an exascale data analytics system?
I'm sure that we do.
If you look in the life science domain, I think the answer is definitely yes. It will not replace the traditional HPC, but if I look in today's scientific literature, the real high impact papers in the life science field, they're developing all in a very much data-driven, large-scale approach way, while the classical applications of classical HPC, they stay more or less constant. If you look at it with the usage of our HPC clusters, the fastest growing part is the one that is driven and informed by data. The other part stays more or less constant. It's not disappearing. So to me, the answer is both, but we're growing much faster on the data side than we grow on the pure numerical model-driven computation side, at least in the life science field.
In the HPC systems we build, we see the same thing. I see the two as a continuum, right? In the traditional HPC modeling and simulation, if you draw a chart of the data growth, you're essentially sending initial conditions in, and then you run your computation and generate lots of data, right? In the analytics side and growing to machine learning side, You're essentially taking all that data, right, plus instrument measured data, right, DNA sequences, outside knowledge, that's even bigger, and then you are trying to converge back to an insight, right, that you hope to discover. So you're actually going through this process in a machine, and then in another machine or the same machine that has both characteristics to try and take the haystack in, and hopefully a needle pops out at the other end. So you're just doing this and that, and should it be two system or one system is still a debate, but definitely we know this right-hand part, right, this next part of data convergence towards the needle is an essential part these days. Yeah.
But are we doing the right investments then? So we had this talk yesterday about, well, the interdisciplinary dialogue when Constantia spoke about the needs in lattice QCD, and it's where there it's very clear. If they have an exascale machine, they will be able to do these computations that will enable them to determine some spins very accurately. And that's, apart from the fact that there might not be industrial applications, it's a simple and clear justification why they need an exaflop. And on the one hand, I guess everybody in this room, we should be thrilled right now because the US, Europe, China, Japan, everybody's throwing money at machines that are larger than ever. But are these the right machines? I feel that when it comes to data, it's very abstract, right? Or should we all rather think of creating machines more like Amazon does?
Mm-hmm. It depends on the goal, right? If the goal is try to get to the top 500, measured by HPL, LIMPAC, it is compute, right? It's actually doing a high compute application, and then you get ranked, based on whether you're number 1 or number 500, right? But there is a new benchmark out called HPCG. Jack Dongara, who is one of the authors of HPL, that's ranking top 500 today, has said, after 20 years of using HPL, we should use HPCG. And there is a separate ranking right now that ranks systems on HPCG, and you'll be surprised, it is memory intensive, that one, more data intensive. Not quite the full, data analytics side, but it's a step forward. And if you look at it, the machines get re-ranked when they go into the HPCG. Yeah. So yes, there is a separate benchmark now to give you a sense of the data capability of the machine now.
Yeah. Maybe Torsten should answer this, because at least in Sweden, these keeps coming up. Like all the life scientists mutter that HPC is useless, or that they can't use the machines.
I was actually wondering if you're asking the right question. So what would, as a life scientist, bring me to use a machine? And the answer is, I don't care about the machine. Maybe, let's quote the House of Lords, not me, but the House of Lords, when they looked at research infrastructures, they said something along the lines of, the real research infrastructure is software and people, and do the right thing with it, and the machine is the consumable. And from a life science perspective, I very much like that approach, because most of our applications, actually none, as far as I know, scales to exascale. What makes a compute center attractive for a life scientist is the data I need already there, pre-installed? Do I have the software stack I need? Do I have people that help me setting it up? Oh yeah, and there needs to be a machine in the background too. So I think we're talking much too much about hardware and not enough about competences and people, and how actually to make these great machines reachable and accessible and useful for the type of applications we want to use them for.
So how should we solve that?
Spend more money on the people that actually run the machines and think much more about how do we bring it actually to the scientists in place. Like you mentioned the Sweden example about the HP centers. We have similar discussions here and in all other countries I've seen in the Alexia network. And somehow there's a complete disconnect between what the life science groups locally at some research centers would like to see as an operational model and as a support model, and what the big compute centers are offering. So we have to both rethink the operational model as well as the training on site. And I'm not pointing to one side or the other as a mistake. I think both sides need to come closer. It's the operational models, how we run the HPC centers, but it's also how we train our life scientists on site, which are, to a big part, looking for a nice word for clueless, but not really well prepared to use this type of architectures.
I always recommend to people getting funding to build supercomputing centers to set aside a substantial amount to hire computational scientists so that they can better use the machine.
So what is substantial? 1 or 25%?
Typically for a world-class supercomputing center, I recommend anywhere from 5 to 10 people. Yeah.
Matthias?
Actually, there are several comments I would have on that. First, I think along the line of what Nuria said, I mean, there's much more data, and then combining it with experimental data would be great. But there's one thing which we have not mentioned, and that already was the biggest thing which NOMAD has to struggle with. And that, in fact, is having metadata. Really define what the data which you have mean. If you look at different researchers in the world, they use not only different units, different energy zeros, they use the same name for different quantities. And so what NOMAD did in the computational material science was defining 1,500 metadata, which are linked, which are connected. That is something which we have to do first, because if you don't have that, you cannot really deal with the data. And that makes the experimental situation so complicated. Coming to the exascale, again, I think it's pretty obvious that different fields or different domains, in fact, have also different requirements. And the metadata needs someone who comes from my field. Your metadata has someone from your field, right? And that having really a bigger machine which creates more data and not defining the metadata is nonsense. What I also think is nonsense, but there probably people disagree, just using the same computer codes and the same methodology just on a faster machine. I think in my field, at least for NOMAD, I think this is not what we want. I think we see in what we are doing in material science, when we solve the Schrödinger equation with some approximation, we see the limits. So what we are doing is density function theory with a certain approximation. If you just use this for the bigger machine, I think you would really not use this investment. You see that this approximation has limits. It cannot do, say, basically the hybrid displays which we have. Hybrid organic-inorganic interface cannot be treated with this. We have to go to the next generation of methodology, to coupled cluster theory for solid, to random phasor approximation, to GW. And I think the big machine has to get together or come together with really new developments. Just really pleasing the computer centers and running the same old computer codes from the 1980s, right? On faster machine, I think would be actually a loss of money as well.
So the comment that I use is, you know, with a faster machine, you don't want to amplify the noise more than the signal, you know, which actually is could be self-defeating. Yeah.
But on the other end, on one level, this is preaching to the choir, right? That everybody in this room, we would all love to have more resources for people and everything. The hard sell is that how do we get the politicians to accept this? Because say what you want about it, although we preach science, both in the US and Europe, a large reason for these investments is, of course, they create jobs. They keep the very large computer companies, Intel, NVIDIA, and everybody in business, right? And saying that, oh, we want more science for it. That's, of course, the scientists will say that. But how do you really convince them, look, take down the hardware investment one notch and invest in people, because that will have a much longer lifespan? At least from my side, that's a much harder sell.
I think for
surprisingly
me,
hard.
the first thing is you have to be honest, right? And if you could do the same thing, if you just would use the same computing codes which we have and just making them a little bit faster, that you could do actually even better on 1,000 petaflop machines. So I mean, you have to be honest, and you should know actually why do you want to go to exascale? And I think not really just to run the things which we have, but to run the next generation of theory. And I think I'm pretty sure that if you explain it, politicians will understand.
Yes, but last week at ISC, it was a debate, a similar debate on the meaning and the usefulness of the top 500 or the green top 500 or the new benchmark. So how could we convince politicians that brains actually have ranking, and what ranking would we use for the people that we want to hire, the brains behind these super machines?
Well, when I recommend that they hire computational scientists to front the machine so that they can then be the interface for the domain scientists to leverage the machine better, I call them essentially the drivers of the supercomputer, right? You need people that can use it well. So for example, without this team, you are using the machine maybe 50% effective. But with this team now, you're using the machine 80% effective. That, you need to somehow quantify it with history, and then that 30% justifies the cost, right, of the people you hire. And so you need to do that quantification for your own site. Yeah? The effectiveness of results, getting results, with or without people. And you can sometimes quantify it because you can look at a code that came from a scientist, and you can look at a code that has passed through a computational scientist. You run the both, you can see the difference, yeah, how long it takes to complete the computation. Yeah, after it's been through the computational scientist.
I would like to challenge the view that it's computational efficiency which is the KPI here. Shouldn't it be scientific output?
And we have to rely on the scientists, right, to provide the starting code of their kernels.
To me, it's a much more important question of what kind of science are we supporting with that infrastructure in a certain country. And the fact that you need an IT industry might be true for the US or for China, but for sure not for Switzerland and Sweden.
But
so I think our
doesn't
motivation might be a different
Doesn't the
one.
funding for the chemists, right, come from a separate source than the funding for the computer, or is it the same
In the end, it's the
Switzerland?
same research ministry which pays for the different streams.
Okay.
So I think we need to get the right balance between having the performance of the machine and the usability and the scientific computing efficiency, but on the other side also what is the scientific output and what kind of science are we supporting, and this is really on the roadmap that we want to follow.
That was a tougher question, right? If the money is coming from one source, and you have to decide whether to buy a supercomputer or hire more chemists or physicists, that's a different question, right? Yeah, I wouldn't even dare to touch that one. Yeah.
But isn't it an even deeper? Sorry, Matthias, go ahead.
That is probably not the issue because actually this money cannot be transferred. I mean,
Yeah,
politicians want a big machine, right? Because that makes them proud and famous. But I think really being honest and using the machine properly and for new methodology and not for old methodology, if you would not do this, it will fire back because at some point it will be known that you're not using it properly, right? And then actually you will lose at the end. So I think being fair and honest in the beginning is very important, I think. Another thing, again, to this data issue is that having so much data, I think, is fantastic, but there are so many methods. I mean, many more than you mentioned, right, in artificial intelligence.
Hundreds,
And if the data, together with metadata, are made available, I think we'll be surprised what people will do with these data if we make them available. I mean, we recently ran a Kaggle competition with some of our data. And within actually 2 months, 800 different groups participated to predict the stability and the transparency of a new type of material. I mean, 800 people with different methods, right? I mean, if you give data to the community, I mean, there will be so much more done with it. And with this, I think it's very important that we also realize making data available. And that has several aspects. One thing, what we did in Nomad later actually became very nicely phrased the FAIR concept. Making data findable, interoperable, accessible, and reusable. I mean, you calculate data, for example, Nuria calculates data for titanium dioxide because she wants catalysis. Right? Someone else actually does it because it's a good solar cell. Another one wants because it's the white in the toothpaste. So actually, if you really have data and you give all the data, you can use it for something completely different. Making data available, and that in fact requires also some other infrastructure. I mean, we now are very happy with our internet, and we are still improving the internet. I think we need a big data infrastructure, that the different HPC centers and the different, say, research institutes really can access all these big data in an efficient way. So creating big data infrastructure should also go together with this creation of data centers, the exascale centers. Right?
But do you even think that it's the infrastructure itself that's a big challenge? Because one thing I realized, and on one hand I agree with Torsten, right? We should measure this in scientific impact. But what I've always felt in my group that, and I think we developing GROMACS in my team and everything, we get lots of both of funding and credit for our software work. But I still feel that all the really high impact papers we do, yeah, that's some PhD student that had absolutely no idea about the code, and they get the Nature paper. And then the poor guys who've done 90% of all the hard work, yeah, they get an implementation paper in JCTC or something. And this is, of course, a problem, right? That how do we award people not just being research engineers, but that if this is important, they need to have strong scientific careers, just as we've had. Otherwise, it's not going to happen. And I feel we're not there in coding and everything, but I think we're gradually trying to get there. In data, I have no idea that, well, you and I have careers, but the people who are going to maintain these databases, will they be able to become professors just from their work of maintaining the databases?
Well, the data saving, curation and all these things, I think that this might be a long-term bottleneck. I mean, for instance, in the European projects nowadays, you are supposed to give all the data, and you have to ensure that this data will be available once the project is finished. But then you don't have funding for this, supporting this data. And that will put severe problems into the way we act or we try to keep the things. Because, in some places you might get support from your HPC. In some other places it might be really, really difficult to get some information, to get some place where to store this, because it's a long term that you have to provide.
Recently in Brussels, one of the EU governing agencies came and we consulted on this, precisely on that point. EU, so basically my suggestion to them was these three things, right? Retain your data, curate it so you label it, right? And then federate it, because the data are in silos, right, in different countries. So the job of the EU is somehow to get intelligence across the silos. So these are the three things. It covers. Then you need to invest to make this a requirement, a required investment in policy. Right? So we've suggested it. Let's see whether it latches on and they actually fund it.
But in a way, you could argue that the industry is ahead of us, right? Because what you said in industry, the companies people pay
Yes.
300 million for now is the data company,
they
not
pay-
the smartest person at programming.
Yeah, and in startup in the Bay Area, right? If you want to have a startup, the first thing the VC asks is, do you have a unified data strategy? That's one of the first questions, Yeah, right? Because they know eventually as companies grow, they silo it, and that becomes defeating for a machine learning system.
So is data a new problem? I get the feeling from the community, or this is my personal perception of the data talks, that we now feel like we have a big data wave because of the computational data that is being generated by these huge machines. But I'm not working with closely with experimentalists in different domains, but I know instruments, experimental devices have existed for much longer than the computing systems have, and the computational science methods have used them. So how did we deal with experimental data in life sciences, in physics, in chemistry, in material science? And can we learn something from there? Or is it just now that we care more because we have both classes of data?
Let me combine this with. So first of all, I think there is a big lie in this whole field. Everybody is talking about sharing data and open science. But if you really look how many people are doing it, it's actually still very, very few. And for example, when in Nomad, we somewhat succeeded to change the culture. There was this request, which Nuria said, you should keep your data for 10 years. But in fact, what people have done, they kept basically the plot after the published paper. They didn't really keep the original, the raw data. And the same is actually in the experimental world. And of course, there is much more information in the data than just this little plot. You do 1 million CPU hours, and then you calculate, and then you publish 5 numbers. There is so much more what other people can do with this. So I think data sharing is very important, and then of course with data and the FAIR principle, making them accessible. Now, when I talk about this data infrastructure to the German research organization, that they should pay for that, but this is not really their duty. Right? They request that this should be done, but it's not their duty to pay for that.
Policy has to change.
Right? And this is what we have to change. That's why I'm saying we need this data infrastructure to keep and make people and make data accessible. And I think for the computational sciences, we could make them accessible in a way that they can be exchanged. For the experimental data, it's actually more problematic. We are working together with people from electron microscopy, and they are creating 1 petabyte per week. That you cannot really bring from the machine to the computer, the big computer. So that has to be stored really at the big machine. But I still think it should be stored, because you still see also scientific misconduct. You still see once a year in my field that people publish something which they have not measured, which was really beautified. And then, of course, you ask them, they said, I deleted my hard disk. I think everybody must be forced that the raw data should be kept, right? And that culture we have to change. And in NOMAD, after quite some dispute, we succeeded in our field, but it's still not really 100% there. And I think in other fields we have to do that.
But it's true that about this big data, I mean, companies, you can go and trace back experiments that were done 50 years ago, and you get all the documentation. They were much better than we academics doing this kind of things, because they need it. They couldn't pay the effort of redoing some experiments that were already done.
Since you're generalizing academics, let me give an example of where it actually worked very well. So it's not all academics. Let's take structural biology, since you mentioned it. The protein data bank is an example of how we actually should do it.
Yes.
That started in the 70s, where there's an agreement that any experiment that is done and published everywhere on the planet that involves structural biology deposits the raw data and the interpretation in one central archive. There's a group of skilled people that actually keeps the archive alive. So even if you go today there and you download the 70s data, it's in today's annotation, it's in today's syntax, it follows the latest standards, it's evaluated with today's algorithms. So we have one consistent field. There was an understanding from the beginning on it's mandatory to deposit, it's mandatory to use semantic standards for context and metadata, and it's free for everybody, anytime, everywhere, which you would call fair today.
Yes.
So there are communities where it works, and they demonstrate nicely that the value of the aggregated data is miles more than each of the individual pieces you could have if you would have them spread left and right.
Who's paying for that?
Who is paying for it? And now we come to the career and the infrastructure challenge. So in the life sciences in Europe, there is an organization called Elixir, that's one of the S3 projects, where we have managed to bring all the European states together in an international consortium agreement for finding ways that all national governments contribute to maintaining these infrastructures. This doesn't cover the full cost now, but there's now a process that is managed by the HFSP, trying to convince the funders that it makes sense to skim a certain part of the research funding for these very basic data infrastructures that we all need to have reference data. This process is going on in Brussels, and it looks like it's going to fly. It works for some of these resources, like PubMed Central, not yet for the big ones, but the discussion has started, and I think it's moving in the right direction, because this giving data scientists that curate data a career path as a PI, as a professor, that just won't scale on the long run. We need a different mechanism for
How
that.
many people is actually working, curating the data for the protein database?
For the protein database, there is 3 teams. There's one in Japan, which is relatively small, 5, 6, 7 people. There is a group in Hingston, which is more in the 20s, and then there's a group in Rutgers University, which is slightly bigger.
I'd like to add, before that, I must state that I agree with Professor Thorsten earlier when he said that when you are torn between funding a machine and domain scientists, hire the discoverers first, pay for the discoverer first, then the machine. But on the matter of data, the biggest I've seen of instruments generating data is the Square Kilometre Array. A few years ago, I was asked to consult on it. When the 2,000 radio telescopes are switched on to emulate a telescope that is 1 kilometer in size, I asked them, what would be a data rate, raw data rate. They said 1 exabyte a day, right? I fell off my chair, literally, at that time, because I just didn't know how to solve it, right? But they have not switched on and built the 2,000 telescope yet. They built probably 20, right? So we built a 100 petabyte storage system for them, right? So that's, down they have a dilemma. Should I keep everything? Should I throw, after spending $1 billion building the telescope, should I throw away 90% of my data, right? Okay, they are all noise, right? Throw away them. But noise could have signals in it, right? So that's why the oil companies don't throw away their raw data. When they go out with a seismic survey, they collect all the mess. I used to be an oil and gas engineer, right? I collected these seismic tapes, stack of tapes after you fire shots to collect the seismic data. Most of it is noise, right? But you don't throw. Because technology improves, and 10 years later, the new processing methods came along and they discovered oil that what they thought was noise, right? So they don't throw their data away.
Yeah, but in oil fields, I mean, they
They
dig
can
with
justify.
20% probability.
Yeah.
So 20% probability you dig.
Yeah.
But I think this is part of the
Pretty
challenge,
low.
right? Because of course we too use Protein Data Bank all the time, and in one way it's an amazing database that Helen Berman and others have been able to have a career out of it. But I think one of the reasons for that is that they curate it fairly hard. It's, as you say, only experimental structures that have been published. So it's still, by any other measure, it's a very small database. But the average quality is exceptionally high.
Structure. Most of them by today, and coming back to your data question, a lot of structures in the PDB are not published.
Yes, no, you're
So in the
right.
meantime, the deposition in the PDB has become the structure. So the data is your publication, not the PDF that you send around to
Right.
your colleagues.
But of course, if we compare this with all these big data companies, that this is a database where you curate first, we know we have a very high quality, the data is highly structured, and compared to industry, it's pretty much the opposite, right? In industry, the strategy is collect everything, and then we mine it and try to curate it later, tag it anyway, and have the computers learn from it. And that's a very different type of database.
But is it feasible to really store all the data and then analyze it later? Because I think, as you mentioned, in the oil industry, 10 years later, I assume that it was 10 more, or maybe a factor of 1,000 more data accumulated.
The fundamental issue is that sensitivity of instruments have far exceeded the cost reduction in storage here, even the cheaper storage. So the gap is orders of magnitude away. So now, today, scientists have no choice but to throw data away. They think that it's noise, yeah? But they are in a dilemma. The SKA team are going through that process right now. I'm sure the electron microscopes and so on, if you don't get enough funding to store and curate that data, you likely throw it away. I mean, do we store today the raw DNA sequence image? We don't.
In Spain, at least, the hospitals, they don't have the tools how to store them. They don't have there will be space, there will be physically space, but the doctors are not trained to do that.
So they don't store them.
Actually,
So they don't store it. I
we
mean,
store
and
the
this is
DNA.
very sad.
We store the DNA, but the problem is you don't get a DNA sequence. The machines actually, they essentially produce a TIFF image.
Yeah.
And from this TIFF image, you then interpret which space is which.
Yeah.
And we no longer store those images because it's too much data. And then we accept, if we doubt it, we have to resequence.
So that's the fundamental thing, the sensitivity of instruments that we are building, right? Far exceeds cost of storage.
But the sensitivity of instruments in the life science is still developing so rapidly that you would rather redo the experiment 10 years later than reuse the old data. So for us, it's often a question of how unique is my sample? If it's a biopsy from a cancer patient, that is clearly something I cannot repeat, so there's no way of throwing anything away. If something that comes from a cell line or a protein preparation or electron microscopy grid,
can repeat it.
it makes much more sense to actually store the grid in the freezer than storing the data on the hard drive.
Cheaper.
Cheaper, much cheaper.
Yeah.
And
I disagree a little bit with this, because this again is in the idea that you do the measurement for a certain purpose. If you would have actually all the, even say all the oil data, maybe actually somebody uses it for something completely different.
Possibly.
Right, and finds it in the noise. So doing this again, actually the oil data will be actually a lot of work also in doing it. So I think we should also find ways to, for better compression and for better storing of data. I mean, in NOMAD we were really surprised. I mean, I expected that by the end of this year we will have 100,000 calculations. We have 50 million now, and I expected we will have 1 petabyte with 100,000. But we have only actually a tenth of a terabyte. And we have 10 terabyte. So at the end, if you really look into what is possible, there are many more options you can do. But again, the idea should be in big data science that you look at data and look for structures without a prejudice what you want to find. And then you will find surprises. Let people do this. Of course, doing things again makes a lot of sense for a certain purpose. But looking for trends, actually it still would be good having all.
Yeah. But there's always the balance of what do I pay for? Like my electron microscopes, if they throw out some 2, 3, 4 petabytes a day, no terabytes a day, is it really worth the effort? And do people dig into this type of data? It's the same question as for DNA sequencers. We don't store the images anymore of the colors changing because we know the data reduction step is good enough that I just need to store the basis and nobody goes back to the original images. So it's exactly as you say. We have to find what is the right level of reducing the signal but not throwing away what we want to look at.
We're doing the same thing. If communication is slower than recalculating, then you recalculate. But still, that does not allow you to do the trend studies.
Yeah, and I agree with you. If you look back in the past, we tried the same with Affymetrix chips. Throw away the raw data, just keep the readouts. And 10 years later, we learned that actually to do all the quality control, we need the original data because the readouts had so much batch effects and biases that were actually useless. So I'm contradicting myself. Yes, it would be nice, but sometimes you just can't afford it.
But for some people and some instruments, they are actually saving not only the raw data, but also freezing the programs that they were using to translate the data into something that is useful, just because it's a requirement. I mean,
Which, in terms of reproducible science, is something you should anyhow doing.
But that's pretty
So
scary.
the failing-
How many
the-
15-year-old programs would even compile on a modern compiler?
So you have to keep the compilers also.
you keep, I think that they,
Yeah.
they actually
But then it
keep
was
the whole
then
thing.
it was made for a VAX that
Right.
doesn't even use IEEE floating point. That
You put it in a container, like a Docker, right?
Be realistic. We're not talking about eternity here. We're talking about 5 to 10 years.
Yeah.
And if you look at the attrition rate of
think that's a great quote.
irreproducibility,
I think the failing is on our part, right? For not giving a step function discovery of a new storage system. We are trying, right? We need a step function change in the way we store data, the technique we store it with. Yeah.
But this is pretty scary, right? Because it's not just a matter of putting tapes on the shelves or
No,
something. Because I even remember when I was a student and you had all these tapes and, guaranteed shelf life of 50 years. Yeah, DDS1. Good luck finding a DDS tape recorder today. That's completely impossible. And I think Torsten is right. Eternity in science is suddenly 5 or 10 years. And that's
Yeah.
pretty scary. So that we have to keep investing just maintaining this data. And then it comes back, somebody needs to have a career funding for this. And of course, the first one to design a new database, they will definitely get the credit, right? The second or third person taking it over and just continuing maintaining it, will they get as much credit? And I think right now we're not rewarding it for them.
And in terms of long-term storage is an issue. In fact, we have a climate science customer, NOAA GFDL. They allocate 30% of their bandwidth in their storage system constantly to move to a new tape. When you look at their site, there is a 30% portion of the machine constantly moving to the next generation of tape, right? By the time they finish this new generation of tape, the oldest one gets to the next generation of tape. And this is how they keep the data fresh here. And that's a climate science site of the order of 100 petabytes today.
So one thing, when it comes to data now, and as I said, we've morphed a little bit to focus more on how we store the data, whether it's experimental from computing and everything, and maybe not going all the way to AI. And since Eng had this great presentation about AI before, let me take an opposing view. AI is amazing in everything it can do. Half of you have probably seen all these amazing cancer predictions, that they're better than the best doctors at Mayo Clinic classifying cancers or whatever. But then we also had these questions about Kepler and the celestial bodies. And being a Swede, I happen to know that growing up in the south of Sweden, we had Tycho Brahe making all these observations. And in one way, he was just a big data person. He collected data, amazingly accurate data, say, on the celestial path of Mars, for instance. And if you look at this, Mars actually makes a very strange, from the Earth, Mars looks like it's making this retrograde motion so that you have a loop in the very, very strange, but exceptionally predictable. And I bet, and of course, eventually Kepler used this to understand that we have a heliocentric piece of the world, but I bet today that Tycho Brahe could just have used AI. So we could have made super accurate prediction, and I bet the AI would have been able to predict exactly when this retrograde motion happened. And somehow that feels like a bit unsatisfactory for our understanding of the universe. And that is a problem, right? And say cancer, of course, if I get a tumor, I'm pretty happy that the computer can predict it. But long term, all the really big advances in tumor treatment have come from fundamental understanding of how cell biology and cell division works.
Yeah.
So are we giving this up because we're so obsessed with short-term gains that the AI can classify things we couldn't classify before?
No, the top-down approach has still to be the gold standard, right? So the bottom-up approach, which is through history, a lot of times it can give you an indication of something new, right? But you have to go back to the top-down gold standard to validate it. Because the bottom-up can't really give you the validation and tell you why. For example, if you go to the FDA and and say, I've got this new drug, and then they ask you why you picked it, you can't say I don't know, right? I mean, because the machine told me. You have to still go back and go through your traditional process. So currently, at least currently, many of the users of the bottom-up approach is really to help guide the top-down towards a new insight. Yeah? But the gold standard still have to be the science approach. Yeah?
Well, on the other hand, if I have a tumor, I like to understand it, but I would probably prefer to get cured
Yeah,
if I have to choose.
but I think we're deceiving ourselves here.
Actually, I learned in the last 2 years that I disagree with this. I was fully in your line up to 2 years ago, but I now disagree. I mean, first, as a side note, Tycho Brahe was Danish, not Swedish.
Yes, I grew up in Scania.
And that was really the great thing. With Tycho Brahe and then Newton and Leibniz, really, they started also having differential equations. I mean, they really changed the whole way how we do physics. And I think we are now changing the way how we do physics again, in the following sense that up to now, we always felt we can describe things in terms of equations, be it Kepler, be it Newton, be it Schrödinger equation. And what I have realized now is that some of the things I'm interested in, be it catalysis, be it also maybe actually some things in medicine, the processes are so intricate. I mean, there is a little thing which can change things, and you're looking at things. It's very, very possible there are many, many things which cannot be described by a simple equation. Yeah. We can find trends, we can find some behavior, but maybe not an equation which you can understand.
Yes.
Right? And so I would say it's a new type of doing science and accepting not everything can be explained in terms of equations, but maybe just in terms of machine learning and trends. And we should be also happy with this. We should not always ask, in your case, of course, I want to see the Kepler equation. Mm-hmm. And the machine is still not able to really do that, and will probably never be able to.
There is this classical quote by Ernest Rutherford that everything in science is either physics or stamp collecting. So you're saying we should forget about the physics part?
Well, actually,
but accepting that it's a new paradigm of doing science and accepting also things are not describable by equation is something we also should do, I think.
in fact, Phil Anderson, Nobel laureate, Princeton University, came up with a paper of emergent properties. I paraphrased him, right? Essentially, he says in his paper, physics cannot explain everything in chemistry. Chemistry can explain everything in biology. Biology can explain everything in physiology. Physiology can explain everything in psychology, and then social science. That's why we have a degree for every one of them at university. At some point, when you go up one level of complexity, your fundamental equations at the bottom can't explain everything above, yeah? Because there is some emergent property. And you talk to climatologists and weather forecasting people, they also believe in this. They use the term emergent property a lot. So this is something new. We don't quite fully understand what that is. And it's related
yeah, but accepting that maybe there is no equation.
Yeah.
Right? I mean, that I think is the new thing. I mean, always, up to a year ago, I was always thinking there must be an equation. I must be able to explain it in terms of some bonding or whatever features. But now actually I'm seeing that some things are so intricate, you better don't really even try for some things.
Yeah. With regards to curing cancer, your comment about it, you want to be cured, that exactly is the point. Because the machine points to you a drug that can cure cancer, that the current gold standard have not discovered yet, right? So it points that out, and then the gold standard then takes that drug, that small molecule, or the long chain molecule, analyze it through the gold standard, and then presents it through the formal way to cure cancer. That's the hope, right? Hopefully that the machine can point you to something new, yeah, by looking at history.
And I wanted to give actually one more example.
Can I directly react to this? Because I'm afraid I have to spoil the party a bit. No big data machine learning algorithm at the moment is able to cure cancer. Mm-hmm. What it does is we have several treatments that all don't work very well. And the parameter space is very huge, and for doctors it's very hard to pick the right one in the right situation. But if you look at it from a global scale, most of them don't work very well at all. So we're trying to optimize a problem which is very bad. So I think there's two things we need to look at. One is this dealing with the current situation, which is very unsatisfactory, and finding in a suboptimal situation a suboptimal solution. On the other side, it's drawing mechanistic hypotheses and going back to basic research and actually find solutions. Find cancer interventions that actually cure. Because most interventions we have today, they just delay dying. But they're not curing cancer. If something cures cancer, it's your body, your immune system, but the chemical drugs we give
suppresses it.
suppresses it for some time, and we might be more or less successful in suppressing it for some time, but we are far away in really understanding cancer and curing it. And that's, I think, where there's the short-term thing of doing the best we can in a situation which is not very satisfactory, but then at the same time using this to learn about what went wrong, what is the underlying etiology of the disease, and then going back into basic research. So it's kind of optimizing the non-optimal, but also generating hypotheses for doing the next step forward. And I think we should not forget the second one.
No.
It's not about just optimizing what we have, by far not.
A remark on the equations. I like very much things that I can explain, and I can explain, and I'm fascinated by those that I can't in order to explain them. But the beauty of equations was because they were in a way, reproducible, right? People could give whatever data in, or maybe the same data in, and then get the same data out. So how could we understand what the machine is? Is this top-down approach, or the data-driven discovery, is that understandable? Is that reproducible? Because I fully agree with your comments that we need to make sure, we need to make the data fair, open, and then what?
Reproducibility of the machine learning method is tough. Yeah, it's tough. I actually went through that experiment, right? The 15,000 days. I use that example because it's simple enough to all to understand. The 15,000 days, we fed it into the machine. It came up with one set of dials, weights. Then we inverted it, sent it in. It came up with a different set, right? That means its prediction capability changed. We took random samples, re-randomized the order of the feed, again different. So it's very difficult to reproduce, yeah? In fact, they also have epochs in training, yeah? You send in the first set this way, and then you repeat sending in again, the weights change again, right? So multiple epochs also change the weights, yeah? And you pull items out for validation set, it changes again. So yes, it's difficult to reproduce and difficult to help validate, yeah? Because you have to go back through the neural network to understand what every stage, how the weights have changed. Yeah? It is changing through a statistical method, right? So yes, much more difficult than having an equation and work backwards from the equation to find out why. So it is still, papers are still being published to try to validate machine learning algorithms.
So it looks like this, trying to understand what the machine learning algorithms are doing generates a new data problem, because if we are to store the weights at every step of their learning, then we just have, it feels like it's a nested concept. We try to understand and then have a big data problem, not that we will use another learning algorithm to try to understand and so forth.
Yeah, I probably have to do snapshots as the machine is learning and the weights are changing.
Yeah.
You know, you tough to store it continuously, perhaps. You do snapshots of it. Yeah, so there are ways to help mitigate the problem. Currently, it is unsolved, yeah.
This is what we're doing currently with large computational simulations, right? We either trace them, or we profile them, or we do intelligent snapshotting of them. So it looks like some methods could be transferred to this community as well.
Yeah.
So we have a few minutes left, about 10, and I would like to ask you, what are we doing wrong? Now we all agree that there is a challenge, and the challenge takes many faces, but what are we doing wrong and what we should not do in the future? Industry, academia, new scientists coming into the field.
I think I was speaking to Rich from NCAR, right? And we were actually talking about the exploitation of machine learning algorithm if we use it wrong, right? Yeah, it's to do with ethics of AI, at least on our side. A lot of discussions with governments have been around that. 1 to 10 years, they are worried about AI affecting jobs. That's understandable. 10 to 100 years, they're worried about how we treat AI systems and how they will treat us, yeah? And how we are exploiting it. So just like any new technology, it can be used for good and bad. But the problem with AI, unlike for genomic sequencing, where government regulation came in and said, yeah, in insurance policy, you're not allowed to use genetic profiling, right? Policy had to step in, right? But the difficulty with AI is progressing a lot faster, right? And people are already using it, even while policy have not started. Just starting the discussion to say, should we implement a policy that you're not allowed to use AI profiling in insurance premiums, right? but it is already probably occurring, right? So these are the kinds of, the issue with AI, different from the time of genome sequencing, is that it's moving too fast, yeah. And policy usually is behind, but now it's so far behind, I believe. But we have to act faster on the policy side.
What are we doing wrong? I think we're pretty good in evaluating the performance of machines, and we're pretty bad in evaluating the performance and impact of humans in this context. We're heavily overselling what AI can do and all this hype around. On the other side, we are not really valuing, as you say, the underlying work that a lot of computational sciences do for enabling all this. I think a bit more honesty and transparency about what really contributes to scientific progress would be something that would make the field more healthy. Also in terms of building careers for younger scientists to see that their contributions actually valued in an honest way and not in the hype way of having the most sexy kind of application, but actually moving the fundamental principles of the area forward. So for me, it's more looking at the people rather than at the machines.
I think, I wanted to say something similar to what Thorsten said. I think really be more honest. I mean, we were all talking about exascale. Nobody really knows what it means, but we're talking about it, and at some point we will have these machines, and then we will do. I think we should do definitely new methodology, not old methodology. We should really use the data, and I think it's a big thing. It always sounds so simple when I say we need metadata. It's a huge effort to define metadata for different fields, and we should also really allocate resources to defining metadata, and that is part of what I call this data infrastructure. We need a European or worldwide data infrastructure similar to what you have shown in the protein database. I also think really in the artificial intelligence, I would think there should be more honesty, because sometimes people really predict that they, or argue they can predict nearly everything. I mean, you said very honestly, your chances are something like 86% or something. 82. 82. That sounds good, right? I mean, typically, say in Germany, we say actually the prediction today is very similar to, tomorrow is very similar to today. That is also better than 50% at least.
Yes, in fact, if it rains today, it's a huge contribution that it will rain tomorrow.
Right. So you also have to really subtract that from the prediction to see what is really remaining then. But we also have to say that in our field, and our means actually Nuria and me, I mean, for example, you look for a better catalyst for a certain chemical. Most likely there are only 5 or 6 or 10 different materials which will do this, from billions of possibilities. So we cannot really live with 90% accuracy. We need actually more than 99% accuracy. So one else has to see the question of what we want to predict. And the same is actually in cancer, right? I mean, also looking at cancer, I mean, different people, depending on their history, respond in a very different way to certain things. So there is so much more to do, and to be honest and to realize that, which I think is exciting. I mean, it's an exciting thing to develop. It's not yet there.
Yeah, I mean, following the message, I think that we need to be honest about it, because that would be good for us on the long term. I mean, I think I have the fear that in 5 years, many people will say, oh, you know, that was so much of a balloon, and people was really promising something that was that they were not able to provide. And then, yes, I mean, we have to improve our methodologies. We have to really train people to be critical with the results, and this is something that I think that we are missing. We have to have these people with mixed backgrounds that can talk to computational people, that they can talk to physicists or chemists. Many of the areas where we can see that there could be a lot of applications will be, if you tag the metadata right, try to use our descriptors or our tags for environmental purposes. That would be great. I mean, being chemist, one of the things that you have to be careful about is how this will impact in the long term the rest of the species, the living matter, and the environment. So I think that there is a lot of work to be done. These very large metadata, so translation between different data of different groups. This is a big challenge, and it requires very good trained people.
So how do we achieve this honesty? Is there a reset button? What's the price for going honest across all fields? When only achievement is the incentive for promotion, for funding, for awards, I don't think anyone has received an award for being just honest, but not succeeding at something.
Well, if you read the Spanish newspapers, there is a cure for cancer every week. There's a cure for cancer every week.
Every week.
One day is pancreas, the other day is breast, the other day is... It's not my field, but you know, I mean, this is particularly because it affects the mentality of the people, and
Exactly.
they really think that this has been cured. Well, maybe in a model of a mouse.
I guess that's what peer-reviewed papers are meant to do, right? That's what peer review does, right? To validate.
Should do at least. Should do at
what
least.
peer review should do, right?
But I actually,
as you said,
there were a
we want
bunch of
sexy physics, but we don't want prostitution journals like,
Yes.
you know the journals I'm probably mean.
Predatory journals.
But one of my take-home messages from this really has to do with how making sure that people can develop, making sure that we reward them for this work. So I have this story from one of the big medical universities in Stockholm that we've been told Stockholm is a bit special in that the medical faculty is a separate university and then the engineering school is a separate university. And this medical university, I think that now for 10 years they've been agonizing about, they know that the data is the future, but they have no idea how to do data. And then eventually, well, have you thought about hiring any PI who is a specialist in data? And then they're like, oh, well, no, they must have an MD degree to work here. And you're not going to solve that problem if you start saying the axiom is that you need to be a specialized surgeon, but they would really like a surgeon who's good at data.
You need this
And
mixed
and I think
profiles.
the only way they're going to solve it, they will have to accept that they will need to have professors who are computer scientists. And that's, to me, it's not a big deal. But for them, of course, they haven't hired anybody who doesn't have an MD degree in 100 years. So that for the entire university, that's a game change. And I guess another thing that ERC grants, right? That we all like to get reward ERC grants for amazing ideas, amazing discoveries. Maybe we need to adapt that if somebody has a very ambitious idea at how to collect a valuable data set or a really, maybe not even a new data set, but a great idea how to curate data, maybe we should push them and start that this is something that is worthy of an ERC grant. And when we hire faculty, we need to step up. Look, we can't just measure Nature papers but this person who seems to have a lower profile, he or she is maintaining a very important resource in the community, and long term, that's going to give great impact for our department, and start hiring them.
Yeah,
Because of course it's easy to say, I want a credit, and then these people should do the work as research assistants. But they will go to industry instead, because they're going to make 10 times my salary if they go to industry.
yeah. My opinion, it needs to start from the top, right, with policy. Yeah, in the same way with the way AI is used, and also hiring and funding. It is top down. We need to get to the governments and convince them that, yeah, AI is where they are today, but they are not everything, one. Two, you need to invest in retaining, curating, and federation of data. Three, you need to hire people appropriately for this area. And also add the comment, right? Same with policy, right? I'm not saying insurance is good, right? But just like in genetic profiling, policy stepped in to stop it, same thing. So I think we put our effort, I recommend we put our effort with the government level and start to change the mindset there because they control the funding. Yeah?
So we have a couple of minutes here, and I would like to open the floor to questions from the audience. If you have any questions for the panel.
Please use the microphone
Okay.
and press
Yes.
the mic button.
So I wanted to follow us up on something Thomas Schultes said, in that there's this interplay between observations and models, that observations drive our ability to discern models. You know, this was clear in early times. And I'm just wondering if you've seen now with the rapid emergence of AI, are there models that have been developed? Because we now see correlation, not necessarily cause and effect, between parameters and outcomes. And is it possible, we've talked about emergent behavior, true complexity, right? Not complicated, but complex. Is it possible that we simply, as the third person over, sorry, I don't remember your name, said it's not possible to develop models for that? I'd be curious to your thoughts on those things.
Yeah.
There was half a sentence which I didn't understand when there was more rain coming on down here. But I think, so first of all, when I said actually there is a paradigm shift that we also accept that some behavior cannot be described in terms of equations or simple models, that I think is a new view. But in principle, I would say we always should try to find an understanding and explanation. And that's in fact why we are using, in addition to the methods which you have described, we are also using compressed sensing in order to find the best physical model. And in fact, that would in fact also find, if we give actually 10 trillion options and then find the two best descriptions. If in these 10 trillion options would be also Kepler's law, we would in fact also identify Kepler's law. But of course, if it's not in, then we would not find it. But in that sense, we try at least to find something which gets as close as possible to a physical explanation. But if there is no physical explanation, the equations which we get are just the best approximation to the trend. So I think we always should start with a machine learning, compressed sensing, or whatever tool. And let me actually just give you one example. It could be that the explanation comes only 100 years later. I mean, my original idea when I started with data science came really from Mendeleev's table of the elements. I mean, this is still the periodic table is still the most important thing in chemistry and physics, I feel. When Mendeleev created this table, rows and columns, he had no clue about the number of electrons. He just looked at weight and he looked at chemical reactivity. And he only had 50 atoms. We now have 110. He had 50 atoms and he knew actually there was an atom which was not called gallium yet. But later it was called gallium, but he knew in fact what the properties of gallium would be, right? From this thing. And so having really data in some structure, and later, 50 years later, when quantum mechanics came up, understanding why is that structure, I think we have to accept that sometimes the explanation may come later when you're not living anymore. So having trends is I think, fine, even without understanding. Trying to understand and trying a simple model is still right. If you have a simple process, I mean, this is the standard way of physics in saying I have a complicated thing, I simplify it as much as possible, and then I can have a model. But in fact, we are now getting to complex things where you can not simplify as much. Catalysis is one example. I mean, you cannot do catalysis under ultra-high vacuum, right? And so you know actually some things you cannot really simplify in terms of simple models. I still think a physicist and a chemist should always try to do this, but you should not be disappointed if you're not succeeding, and I think a paper should not be rejected if there is no explanation. If there is a good trend, I mean, as a theoretician, if you don't have an explanation, as a theoretician, the paper will be rejected. If you're an experimentalist, actually, that's still okay. But I think actually with this type of new paradigm that maybe there is no simple explanation, we should also accept that.
So policy change.
Review our
Let's
policy.
see, not yet there.
Not yet, okay. Maybe in that respect,
I think we might have time for one more question.
Hi. I want to thank all the panelists for the very nice discussion. I think another perspective that is very important is the perspective of the people or the students who are actually working. And I was very happy that it was at least acknowledged that there is some sort of a problem, because while everyone is being motivated to work in this field, develop methods to implementations, there is not enough credit being given to the students. And at this point, I want to say that now that you've already acknowledged that not enough credit is being given to people who are actually doing the heavy lifting, how do you want to motivate them while those people already know that they are kind of doing an ungrateful job?
Yeah, that's a good question.
Yeah. Firstly,
Probably the $1 million question even.
Firstly, the students are not being paid as well as compared to if you join Google, for example, already, right? Oh, I see. Yeah. Well, I guess you climb up the ranks, right? Yeah. So you're saying you're doing, in the labs, doing the heavy lifting, but are not being recognized. Do you all get your names in your papers also, in the papers published?
Yes, but I mean, for example, people who actually do like write codes and actually maintain code and actually do implementation.
But I think the analogy
that-
I had is a great one, right? You might have a team who does a lot of really hard work. You spend 8 years, and then you publish the implementation in a low-impact journal. It might get heavily cited 10 years later. And then you have one more student coming in the lab using this program, and it's the second publication that gets into Nature. That student is going to have a great career. The first one, on the other hand,
Doesn't that student
Honestly, I think actually I always try that a student, even if the student is doing, say, 80% of development, there should be 20% in demonstrating this thing. And that together actually makes it into the top journals.
and maybe even forcing these students to lead some of the very high-impact publication, high-impact application papers, because they did all the heavy lifting on the development.
But one thing where I have problems, but you mentioned, and also in getting really the right infrastructure in my group, is having actually people from computer science.
Oh, yes.
We are unable to pay them.
Well, if you're unable, imagine us.
And that is really, I mean, we need really top people in this field, but actually there are far too few. And we all have to educate more of them, really, that they also have fun in doing this.
Well, that's a big problem in AI, right? That I heard this, it might be a year or two ago, but basically anybody who has a PhD in a relevant AI field in the Bay Area, you will get $1 million from Google.
we can't
Like,
even
so
hire them.
even the professors are leaving Stanford and moving to Google and Facebook.
Yeah. So the key is we must treat machine learning towards artificial intelligence, just one method of getting intelligent, as a new course, right, that everybody takes, like as though you did programming.
Yes.
It must be treated like as though it's programming, right? Everybody did, for example, Fortran programming if you are either a scientist or engineer, right? You should do the same with AI.
That's considered cruel and unusual punishment nowadays.
Just treat it as a language you learn, right?
So-
That, you know, if you learn French, right, you learn Fortran, right? Or now you learn TensorFlow, right?
Yes.
So, yeah.
Yes, languages and programming languages are just a programming word away. So we are reaching the end of our nice panel. I have just one message for the young people here. So professors are moving to companies. That means that there is room for you to come into the university pipeline and get the new professorships. But also don't forget about computer science, while all these other topics are very important. They need you, and yeah. So keep that message while we hand off to the next. It's going to be a flash poster session, and many students will be there. So we'll see. We'll support them. But please, let's thank the panel for a very interesting and provocative discussion.
Thank you so much.